Okay, so this section's about the annihilator. So let's assume that y is some function of x. We're going to define big D raised to the k of y to mean the kth derivative of y. So derivative here would be with respect to x. So note, say we have this differential equation here, y double prime plus 5y prime plus 6y equals 0. We could replace the y double prime with d squared of y, because the d squared means second derivative of y. We could replace the y prime with dy, because d means derivative of y. And then we'll just leave the 6y as it is. We could then factor out the y here, because the derivative is a linear function, so therefore we could write this as d squared plus 5d plus 6 times y equals 0. So we call let's call it L, the d squared plus 5d plus 6. So this guy here is called a linear operator. So let's generalize this idea now. So in general here, L equal to an here is a constant, d to the n plus an minus 1, d to the n minus 1 plus dot dot dot, all the way down to plus a 0, is a linear operator. If L of y here, L some linear operator, so if L of y is 0, we say that L is an annihilator of y, or it annihilates y. So if we look up in this example up here, the d squared plus 5d plus 6 annihilated y because it equals 0. So the d squared plus 5d plus 6 would be an annihilator of y. Okay, so let's take a look at the theorem now. So I'm going to erase stuff here and look at theorem 10. Okay. Okay, so here's theorem 10, has two parts. So part 1 says d to the n annihilates each of the following functions, 1x, x squared all the way up to x to the n minus 1. Here n is some whole number. Okay, 2, d minus alpha to the n annihilates each of the functions, e to the alpha x e to the alpha x, dot dot dot, x to the n minus 1, e to the alpha x. Okay, so let's get some intuition here before we look at the proof. So just to give you some intuition, so let's choose n to be 2, say. So part 1 would say then that d squared should annihilate 1 and x. So let's see why that's the case. Well, d squared of 1 means the second derivative of 1. Well, the first derivative of 1 is just 0, so therefore the second derivative would be 0. So annihilates 1, d squared. And let's look at d squared of x. So d squared of x you can think of as d of x, d of x. D of x means first derivative of x, which is 1, and then derivative of 1 would be 0. Okay, so that's, we've kind of shown 1 for the case when n is 2 anyway. Okay, now let's go back to the general proof. Okay, so let's start the proof. Okay, so let's start the proof here. So first note, in 2 here, if I let alpha equal 0 in 2, we get 1, I claim. Why is that? Well, if you put 0 in place of alpha here, I'll have e to the 0. E to the 0 would be 1. Here you'd have e to the 0. X times e to the 0, you have x. Then you'd have dot dot dot. 0 in place of alpha here, just be 0, just have x to the n minus 1. So you can see if alpha is 0, it becomes exactly this up here. So 1 is basically a special case of 2. Okay, so we just need to prove 2 now. Okay, let's keep going. So again, hence we'll need to prove 2. So to prove this, because this n could be any whole number, we need to use induction. So to prove something by induction, we're first going to show that when n is 1 it holds. and then we're going to assume it holds for n equals k, and then show it holds for n equals k plus 1. So it's kind of setting up a domino effect. So showing the n equals 1 case works, and then if the k case works, then the k plus 1 case will also work. So it sets up like a domino effect. So the dominoes will keep going down. You set up a chain reaction, and that's induction. Okay, so let's first show n equals 1. Okay, so I'm going to prove the n equals 1 case. So when n is 1, we must show then, so this guy, when n is 1, we just need to show that d minus alpha annihilates e to the alpha x. So we need to show this. Okay, so note here, d minus alpha times our e alpha to the x. You can distribute our e in there. So it'll be d of e to the alpha x minus alpha e to the alpha x. And again, the d means derivative. So the derivative of e is itself times derivative of alpha x with respect to x. So it'll be alpha e to the alpha x minus alpha e to the x, which is 0. So this proves then n equals 1 case. Okay, now let's assume it's true for n equals k. Okay, so now we've shown the n equals 1 case. Now we're going to do the induction part here. So basically we're going to assume that 2 holds for n equals k. So that means that d minus alpha to the k times x to the m e to the alpha x equals 0 for m between 0 and k minus 1. And then we're going to need to show the next one up. So the next one up would be then the k plus 1. So d minus alpha to the k plus 1 annihilates. We need to show x to the m plus 1 e to the alpha x, where again m is in this range. Okay, so I'm out of space here. So let me erase a few things and we'll keep going. Okay, so summarizing, we're assuming that d minus alpha to the k annihilates x to the m e to the alpha x, where m is between 0 and k minus 1. And we need to show the next one up, so therefore the k plus 1 guy annihilates the x to the m plus 1 e to the alpha x annihilates this, so equals 0. So assuming this here, we have to show this one. Okay, so let's start doing that. So note now, so we need to show this guy 0, so let's start working on it. So d minus alpha to the k plus 1 applied to x to the m plus 1 e to the alpha x. I can break this up as, so I want to use my assumption up here. The assumption has a d minus alpha to the k. So let's put that there. So I'm just basically taking 1 away from that, so I'll put my d minus alpha inside here. So just breaking up the d minus alpha to the k plus 1 as d minus alpha to the k times d minus alpha. Then distribute this guy, so it'll be this times my d, this times my alpha, which I've done here. And again, the d means derivative, so we're going to have to use the product rule on this, because we got 2 functions of x here. So let me write it down here. Okay, so applying the product rule to this, so the x to the m plus 1 is my first function, the e to the alpha x is my second function. So the derivative of x to the m plus 1, bring the m plus 1 in front, subtract 1, x to the m, times my second function, plus first function times derivative of e, so it'd be itself times derivative of alpha x would be just alpha e to the alpha x here. So that's my product rule there. And notice these two are both the same actually, because that alpha can bring over in front here. So these two terms will cross off. So then we have, so these cross off, so then we just get d minus alpha to the k times m plus 1 x to the m e to the alpha k. Now the m plus 1 can come outside because this is a constant, so I can pull it out in front here. That'll be d minus alpha to the k x to the m e to the alpha x. But up here we're assuming that's exactly the same as this. We're assuming that that's 0. So this guy is 0 by our assumption. So let me write that. Okay, so again, this guy is 0 by our assumption up here. So therefore, be 0 times n plus 1 would just be 0. So he's shown then what we need to show. So he's shown that d to the alpha to the k plus 1 of x to the n plus 1 e to the alpha x is 0. So hence, claim follows by induction. So we're done. All right, so let's leave it there.